Okay, everyone, this is Mr. 13 Things, or Sounds Did Good, depending on which channel I'm pushing this up on. And I'm in the middle of doing a quaternion multiplication, which is multiplying a quaternion number or a Hamiltonian number, which is comprised of a real vector, real giving in yellow, and then a three-dimensional imaginary vector with the directions being I, J, and K. You'll tend to map these to real space, being the X, Y, and Z direction. But however, we're just doing the mathematics of how to multiply them together by hand, knowing that you won't do it by hand very often. But we're also going to do a review here by now multiplying the value of this quaternion times this quaternion, which is that value there, times the conjugate of the first quaternion. So the conjugate of a number is essentially the number that multiplied by the other number gets you the magnitude of the number squared. That's a little confusing, so we're just going to show you how you write it. What you do is you switch the signs on the things that accompany the real numbers. So I'm going to go ahead and realize that we're going to put a 1 here, but we're going to put a -2, a -3, and a -4 in the other places here. And we remember that this is now, remember the I and the J. And what I'm doing is I'm taking this, so I did that wrong, so I'm going to do an edit undo and edit undo. This is I want to do -2, -3, -4. So I'm grabbing the color to keep this set. So once you do this a while, you're not going to be switching color, but it's a nice idea as you go through to keep track of these, especially in here by color. So -2, and I'm going to catch that, and then a -3, that's that, and then of course finally what you're seeing off on the side is I'm going to pick up the ink eyedropper tool, -4. Okay, now we're going to go, once again, we're going to do the math in the squares, which should tie you back to this idea of the lattice method. So hopefully maybe on the side I'll put a link to the point where Vi Hart, the sister from another planet, talks about really multiplying two numbers together is just multiplying each part of each number by each part of the other number. In these cases, the parts are different components of a vector, some of them real, some of them imaginary. Very often when you're doing this, it can be just breaking up the number 8 to 2 plus 6. That's called algebra. Okay, so now I'm going to first do the real part. Once again, I'm going to go ahead and pick that up, and I'm going to get my pen. So the real part is 1 times -60 is -60. And here's what's going to be interesting. When we end up with this, we should have all real components, and I think no imaginary components by the time we're done. So let's just see whether that's the case. All right, so that of course is a negative number, and this is going to be -2 times 12, which is going to be -24. But remember, we have to put a minus in each of these because they're the I squares, J squares, and K squares, so they're going to end up flipping into be positive, and so we have 3 times 30 is -90, right? So there's the -3 times the 30, and the -4 times the 24 is 96, right? So -96. Of course, these all become positive numbers, but we're keeping track of the multiplication of the component directions separate from the multiplication of the coefficients. So we've done all of the real components. Now we'll do the I components, which more or less were mapped from the X direction, if you think about what we are often doing with this. But so now we have 1 times 12 is 12, and -2 times -60, so that's real, and this is real, so this is 120. And now we can, all of a sudden, oh, we realize over here there's going to be negative. We'll review in a little bit. That's the negative up there. We have -3 times 24, which is 72. And it's negative. This time it's negative, but we're running out of space there. So I'm doing a little bit better with my underlay. And I'll show you now one of the reasons I have this laid out the way it is, I'm turning layers on and off, is that effect. All right, so minus 72, of course, that's a negative, and this is going to be positive, and this is 30, so this is minus 120. 30 times 4, which is minus 120. And as we start looking at this, we can get a little of intuition here that this is not going to be as I said, I don't think. I don't think this is going to turn out to be no I component at all, so I'll be wrong with that intuition there. We might be wrong, but let's double check our math here. 12 and 120 and minus 72, which is going to be a plus 72, and this is minus 120, which is going to be there. Okay, so we have that. So I'll be wrong on my intuition about what a conjugate is, but you do get the conjugate by using a minus, minus, minus here. And we'll check our numbers are correct. And so I'll kind of hopefully correct these. I'll probably still put this out even if they're wrong. These were wrong. The additions, these were correct. I checked them in a calculator. When I took the values over to here, that might have been screwed up. But let's now go on to the green direction. This is why you'll start to learn to trust some checks in your calculations. This, of course, is going to be 30 times 30, the j direction, or the j component times real is going to be j, and this is going to be the real component times j, so this is 180 positive. If you remember looking over here where you had the negative sign was down there, we'll double check that in a second. So we have, in this case, we have minus 48, right? And the other place was over here, and you start to see there's some nice visual patterns here. This is minus 48. And so those end up washing out on each other. So we're going to see that my intuition was not correct, or maybe it's correct only in the two-dimensional number of the real imaginary plane. All right, so we have those two done, and now we're going to go finally with the blue. We're going to suck the blue up. We're going to do the blue or the K direction, and we're back to the pen here. And we have 24 times 1. These are obviously positive, or have no sign changes because a real times an I is a real. And this is going to be plus 240. Those are, now in this case, the one with the negative sign is there, which we're going to go back and review these once we're done with the calculation. You have minus 60, and you have minus 36. Now, let's check our values up here. So, in other words, let's check the places where we think that the multiplication ends up with a negative number. So this case, it's, remember, real, I, J, and K. So the J direction, fingers pointing towards up the Y, the J direction times the I direction is going to get you a negative K direction. That one's good. This one is the I times the K. You I times the K, you get a negative J. That's correct. And the third one is here, which is the K times the J, and you get a negative I. So those indeed are correct, and we end up with, again, adding up all of the numbers. So this becomes minus 60, right? This is plus 90, plus 96. So we have plus 24. So we have 60 plus 24, minus 60 plus 24 plus 90 plus 96. Right? So that's going to get our real number. For the I direction, we're going to have to add up these. So we have 132, and then we have minus 120 plus 72, which is going to be 48, a negative 48. And so we have 132 minus 48, which is something in the order of 80 something. So I'm going to pause the video here and do the addition. I know I should do it by hand, But we're going to see in the next video how you can write some script and some programs and whatever else to do this using the ability of multiplying matrices together and just pulling out particular cells, if you would, or particular products. So it has to do with the different types of products of multiplying vectors together. You know that a row vector times a column vector gets you a single number, but if you do it a column vector times a row vector, you get something that looks like this, a 16-place vector if it's a 4 and a 4. So I'm going to hit pause here, and then I'm going to come back. Okay, I plugged that into my calculator and came up with an answer of 150 real, 84 plus 84i plus 210j plus 288k. Now the conundrum comes in. I can't say that I know the answer. I thought that if you multiplied a set of numbers in the sandwich product, and that means what we saw here is that we took the value of this calculation, which is a quaternion 1, 2, 3, 4 times a quaternion 5, 6, 7, 8, with the yellow being real, the red, green, and blue being the I, J, K coefficients. You took this answer, you plugged it up here, and then you multiplied by the conjugate of the original rotation, or the quaternion. My intuition was that would end up being a real value. That's because that's the way it works in a two-dimensional real imaginary plane. That did not seem to be the case in this calculation. I will post if I'm wrong, but I will still probably post this out for this reason, to review. A real times a real, we're going to review those here, and I'm going to try to do it color-wise in yellow. So I'm sucking up the color. So we know that a real times a real equals a real. We know a real times an I equals an I. A real times a j equals a j, and a real times a k equals a k. We know that an I squared equals -1, a j squared equals -1, and a k squared equals -1. We don't have an ijk multiplication here, but we also know that ijk equals -1. But we do know this, that I times j, and I think it's usually a cross, equals k. We know a k times I equals a j, and we know a j times k equals an I. See this, an I times j equals k, a k times I equals a minus j, and then a j times k equals an I. And you start to see this plus minus plus pattern come in, and you'll see as you start doing forwards or backwards, learning to do what's more normal three-dimensional math, which is just basically transformations and rotations about the x, y, or z axis, or if you would, mirroring or reflecting around any given plane based on the first one for rotation being cosine minus sine, sine cosine, except for when you go and do about the y-axis, when you switch the sign on the sine. So you start to see this plus minus plus pattern emerge a lot. And so what we saw here is how if we know I times j equals k, then j times I equals minus k. And we did the signage for those kind of multiplications up here on the right. Otherwise, we're just multiplying this number, which has 4 components, by this number, which is 4 components, multiplying each number by each other number and coming up with the answer that leads to here. So this ended up going to there. All of that turns out to basically go to there. And then we multiply by the conjugate. So the conjugate. And the conjugate is basically the real number remains the same, and you flip the signs on the imaginary portions. That's another way to basically define the conjugate. It's probably the one that's going to have to stick. Thanks for listening. We'll pick this up and keep applying this now with a lot of trig involved.